Hi, this is Sung. I'm your online maths mentor, and in this episode, basically what I want to do is go through a little bit of an aside and talk about different ways of expressing acceleration. Now, you will find this on your reference sheet, okay, and it will be at the top right-hand corner of page 4, okay? So if you look there, right, basically you will see that acceleration can be expressed in all of these different ways. So just check your reference sheet for that, okay? But in order to kind of get to that, let me just go back and just explain some of the stuff that we already know. Now, what we already know is this: if you have X representing your displacement or your position, then when we differentiate that with respect to time, we get velocity. When we differentiate it again, so the second derivative of displacement, you get acceleration, okay? Now, because acceleration is the second derivative of displacement and velocity is your first derivative, we can just as easily differentiate velocity with respect to time and get acceleration as well, right? So that's what we already know. Okay, so the first two parts of what's there on the reference sheet we already know, but I also want to introduce you to the next two bits, right? Because this can be particularly helpful, especially as we go through the next part of what we do, which is going to be on, simple harmonic motion and other forms of motion, okay? And this will be particularly useful where the velocity is expressed as a function of the displacement, okay? So the velocity is going to be expressed as a function of the displacement as opposed to time, okay? So rather than dv dt, it's going to be dv dx, right? So when that's the case, right? So when you've got velocity as a function of displacement as opposed to time, we can work out that the acceleration is going to be v times dv dx, or it's going to be the derivative of half v squared dx, okay? So I'm going to show you how these two things work, and then in future episodes we'll basically go through some examples where we use these sort of stuff, okay? So let me go through how we get to that. Essentially, we're going to use the chain rule, right? So the chain rule says this: when you are working out the derivative of some complex function, right? So some function that has many parts to it, what we do is we can introduce an intermediary variable. So in other words, a variable in between your y and your x. Let's say that variable in between is u. Right? And then we use the chain rule to work out the derivative of y with respect to x by using the derivative of y with respect to that intermediary variable, which is u, multiplied by the derivative of that variable with respect to x. And what you'll notice is, just like any sort of fraction, the du's and the du's will cancel, giving you the derivative of the overall function. Okay, so the way it works in practicality is that when you've got, say, a function where you've got many layers or many shells, you basically differentiate from the outside shell in, okay, which is essentially what the function of a function or the chain rule is. So we're going to use that with what we already know. Now, what do we already know? That acceleration is the derivative of velocity over time. Okay, so we're going to introduce an intermediary variable to kind of get to these two results. So let's have a look at the first one here. All right, so we know that the acceleration is equal to dv dt. So let's break this up. dv over something times something over dt. Okay, now in this situation, I'll use a red pen as well. We're going to introduce the x, right? So it's going to be dx here and it's going to be dx here. Got it? Now, what do we know about dx dt? Well, dx dt, of course, is your velocity. So basically, the derivative of your displacement is going to be velocity. So that goes here, velocity, times dv dx. So that's your acceleration. Got it? Let me come around the other side. So the acceleration, another way of expressing the acceleration is your velocity, yep, times, well, dv dx, which is that one over there. Do you see that? Okay. We're going to do something very similar. We're going to use the same technique to work out this one over here. All right, so let's start off with this. Your acceleration is equal to v times dv dx. You got that? And we're going to introduce another intermediary variable in this situation, one that's going to work really well, is dv. So that dv there is going to cancel with that dv there, which means we've got to put something here. Now, what's going to go in there, right? I'll tell you what's going to go in there. It's going to be, right, because we're differentiating with respect to v, the primitive of v, right? So it's basically v, and I'll just write here primitive. If you don't get that, let me just show you another way, right? So we've got dv of some value. Let's call that like, let's call it, say, capital X, right? Let's work out the derivative of that capital X. Now the derivative of that capital X is going to give you v, right? We want the derivative of that to equal v. So to work that out, right, you've really just got to find, so the derivative of v, or so the integral of v with respect to d is going to give you that, right? X. It's going to give you that x. Now what is x? X is really just the integral or the primitive of v, right? So let's work that out. So x is going to be equal to the integral of v dv, which basically is, so add 1 to the power and divide by the new power. Got it? And then you got the plus c. Right, but you don't have to worry about the plus c. So it's that there that goes into there. So that, can you see how that x is going to be the primitive or the integral of the v? So what we end up with, okay, is dv a half v squared times dv dx. That will cancel with that, leaving overall that. Okay, so that's how we get to that. All right, so just make sure that you understand it, and we'll be using these two formulas in, or these two derivatives in the next episode. Okay, thank you very much for watching. Bye.